Testing on YouTube. 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 Testing. 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 Okay. Works on YouTube. How's it going? Rahul, Sarah. I think Michael was also saying something. All right. I think we should be live on X as well. All right. I think we're live on X. Let's double check. Make sure that's working as well. Profile. Testing on X. Okay. It's working on X as well. All right, perfect. We got all the streams working. Let's take a sip of water. We got something different for you guys today. We got not a didgeridoo, but this is called a shofar horn. It's like a goat horn. This one is a little bit harder to blow than the didgeridoo, so it might take me a couple tries. It also is a lot more high pitch, so we'll see. That's a shrill horn. All right. Welcome to another Hupo stream. We're going to be doing something a little bit outside of my expertise. Maybe not a little bit, but a lot of it outside of my expertise. This is called Generative Molecular Dynamics. Specifically, this paper here, Generative Modeling of Molecular Dynamics Trajectories. This was recommended by one of our Discord channel members. Apparently, it's pretty cool. So that's what we're going to be doing today. We're going to be diving deep, trying to see how generative AI techniques are being applied to, in this case, molecular dynamics, which is kind of like chemistry, biology. But yeah, I mean, I'm not an expert in bio or an expert in chemistry, so if you guys have expertise in that, please don't judge me too hard. You know, I'm just a guy trying to learn. So, Captain Hupo on board. I appreciate it, God buddy. How's it going, Sagar and Sotaki and Jamal? Question from Sagar right off the bat. Hey, will Gen AI replace a coder like us or just IT tool? How to survive this market? Yeah, so I mean, software engineering has effectively been my job for over a decade at this point. You know, that's people ultimately pay me for software engineering. So I have those type of doubts as well, where I see AI tools getting better and better and better. And at some point you feel like you're just fundamentally going to get replaced. But I think the right way to think about it is that people who don't know how to program are not going to know how to ask a coding agent to do what they want, right? So no matter, think of it as AI gets better and better at coding, you actually get more and more powerful as an individual human coder, right? So now when I work on software projects, it's almost like I have multiple like junior devs underneath me, right? And my knowledge of software engineering allows me to better manage and control these software agents. So rather than having this kind of negative mindset of like, oh, well, I'm going to get replaced by this software agent, instead think of it as I'm going to get extremely augmented by this software agent, and I'm going to be able to do 10 times the amount of software engineering work that I used to, which means in a way I'm actually going to be 10 times more valuable, right? So yeah, just get used to using the tools and you'll get more done than anybody. And at the end of the day, like, you're still going to be valuable because people will just come to you to do software stuff, and you will effectively be the interface to software agents. Yeah, in a way. So, I mean, you could think of it like farming, right? Like at some point you had mechanized farming, and if you were someone who like farmed by hand, you could feel threatened by that, right? You could be like, oh shit, I'm like, this machine can farm so much more effectively than I can, like I'm doomed. But the reality is you actually still have a lot of farming knowledge, right? So if you get one of those machines, now all of a sudden you can farm 10 times the amount of land that you did before, right? And all that farming knowledge of like when to plant, when to do things, oh, you need more water here, like this soil is good, this soil is bad, this plant grows better here. Like all that farming knowledge is going to be augmented. So yeah, don't worry about the AIs replacing you. Instead, use the AIs to become kind of like a one-man army that can do all kinds of things. Okay, so let's go back to this paper here. This was released 26th of September, 2024. This is from MIT. And I pulled up here the open review. So these papers, right, part of the whole scientific process is that you want to get peer reviewed. And this is effectively just anonymous reviewers that reviewed this paper and basically had to give it a score. So if you don't know enough about a specific domain, such as me, like I don't really know enough about molecular dynamics to like judge the quality of this paper, you can usually pull up these reviews and kind of see. Sometimes these reviews aren't great. You know, there's a lot of memes about these reviews being terrible, but when you go here and they say rating 9, top 15% of accepted papers, strong accept. Rating 8, top 50% of accepted papers. So it does seem like the reviewers who, in this case, are going to be experts in this field say that it is quite novel and interesting. So novel and non-trivial. Work is very exciting, high potential for impact, and deserves easy acceptance. Okay. So I'm convinced, right? We got someone on our Discord saying that this is a great paper. The reviewers are saying it's a great paper. It has generative AI in it, so let's see what's going on here. We're going to start off with the abstract here. Molecular dynamics is a powerful technique for studying microscopic phenomena, but its computational cost has driven significant interest in the development of deep learning-based surrogate models. So, generative modeling of molecular trajectories. What the hell is a molecular trajectory? So I have some GIFs here. This is a molecule, and you can see it is has a certain states over a sequence of time. So the states over time is a trajectory, right? So there's a trajectory associated with this molecule, and you can see that it's trying to fit inside this kind of binding site. Right, here's another example of that. And this kind of ball and stick model, right, is maybe a little bit misleading because sometimes it's presented more like this, right? But this is also a kind of molecular trajectory. You see this molecule is kind of changing and evolving, and the structure of it has some trajectory over time. And then if you want to get super fancy, here is a bunch of molecules. I think this is actually how you get the rotation of flagella, right? So some bacteria, the way they move around in this kind of like the liquid medium that microbes live in, they have these little like flagella that spin, and this is the actual molecular mechanism that creates that, right? So this paper is effectively about generating these molecular trajectories with transformers and other types of generative AI architectures. Okay. So they're going to be conditioning on appropriately chosen frames of the trajectory. What does that really mean is that there's a bunch of different kind of ways to think about what it means to model or generate the trajectory of a molecule, right? So you can have, for example, forward simulation. Forward simulation, you just start with a static frame, right? This is just a snapshot in time of this molecule. And then I want to know what it looks like 1 second from now, 2 seconds from now, 3 seconds from now, 4 seconds from now, right? So you're starting from one frame and you want to kind of generate the next frames, right? Kind of the same way that a transformer would, you give it some amount of words, some sequence of tokens, and then it predicts the next tokens. That's effectively what you're doing in forward simulation. Interpolation means you have the first frame and the last frame, and then you're filling in the middle frames, right? So that's kind of like a masked modeling, right? Where you have the first and last frame, and you fill in the rest. But this is also useful for if you don't know the middle, right? So imagine if you had the initial state of a molecule, and then you have the final state of the molecule where you're like, okay, I have this molecule, and then I want it to fit inside this particular binding site, which I know kind of looks like this. So how would it even get to that particular binding site position or state? Upsampling, which is kind of the same thing as interpolation, but you have some of the intermediate states as well. And then inpainting, where you might have the whole trajectory, but you don't have the trajectory of some specific subcomponent of it, right? So maybe the way that you're measuring this or calculating this, you kind of know what the outside of this is doing. Maybe you don't know what the inside of it is doing. So this will allow you to generate what the state of that molecule is for like some specific sub chain within that, right? So you have a trajectory of 3D coordinates, right? You have frames, and then each of these T frames, so the trajectory is going to be a sequence of T frames, and then L residues. Residues are basically like each of these little chunks. So there's kind of this natural discretization, right? When you're dealing with language, right, feeding language into a transformer model, you have to discretize it into little chunks, and those little chunks end up being little chunks of words like this, right? So in molecular dynamics, there's already a very obvious form of discretization that the universe has created for you, and that's basically these little chunks here, right? So I don't exactly know what one residue is, but I assume it's probably like one or two little pieces of this. So this might be one residue, and then this here is another residue, and then this is another residue. So now we've fundamentally broken the problem down into something that looks very familiar for generative AI, which is, okay, we have a sequence of T frames, and then each of those has some residue, which is like one out of a possible set of however many possible residues there are, right? I don't exactly know how many residues there are. Maybe there's 20,000 possible residues. Maybe there's 100,000 possible residues, but, right, they're from some limited vocabulary of all residues that are available. All right. So they're going to be conditioning on part of the molecular system, and in painting, we also demonstrate the first steps towards dynamics conditioned molecular design. Okay, so once you can kind of predict what the trajectory or the dynamics of these molecules are, maybe you can start designing molecules that have some specific trajectory, right? So if you're designing some kind of drug and you know what that drug needs to do, right? Maybe it needs to go into this binding site and then push this little thing up here or something like that, right? A lot of, like for example, in this one, right? You're like, okay, we know that this thing needs to rotate, but we don't really know like how it rotates. So let's put it here, and then we'll get the interpolation, and now we kind of more fundamentally understand what it's actually doing, and then maybe that allows us to design a different molecule that would fit better for this particular use case. So as soon as you can model these things, right, then you can start feeding that back into the design process. And there's one really important part in here, which is this idea of computational cost that we'll touch on later, right? Because there's nothing necessarily novel here in terms of the fact that molecular dynamics, there's lots of different techniques that people have come up with over time to be able to predict and generate these molecular dynamic trajectories, but it's always come at a very high computational cost. So almost the benefit of using generative AI for this is that you're going to be able to do this in a much more efficient way. And then once you can do it in a much more efficient way, then you can search through a much larger amount of possible trajectories and molecules, which allows you to find the solution that you want better. Okay. Let's keep going here. MD is computationally demanding due to the large separation in timescales between integration steps and relevant molecular phenomena. Right? So, how's it going, Emily? Emily is the person who suggested this paper. So let's kind of skip over that because I think it's better described later. I'm going to try to be a little bit more linear today. I feel like past couple streams I'm bouncing around too much and I just spent a lot of time just trying to find specific things that I read, but this time I'm just going to kind of go straight through the whole paper, and I feel like that'll be easier to follow. Learning surrogate models of molecular dynamics has become an active area of research in deep generative modeling. And MDGen, which is this paper, right? So molecular dynamics generated the generative version of this, right, with deep learning, is a novel paradigm for fast, general-purpose surrogate modeling of MD based on direct generative modeling of simulated trajectories. Okay, so you're directly modeling these trajectories of these molecules. End-to-end generative modeling of full trajectories viewed as a time series of 3D molecular structures. Okay, so pretty much just repeats of everything we've been saying here. Okay, and then these are the 4 different types, right? Forward simulation, interpolation, upsampling, and inpainting. Which is kind of annoying, right? Because it's like there's analogous terms in generative AI for these types of things, like masked modeling, right? But here they call it interpolation. So a lot of the same ideas. The way they're going to formalize this is as a generative modeling task over a 2D array of SE3 invariant tokens rather than the residue frames or point clouds. Okay, so what is SE3 invariant tokens? So we're going to maybe jump. Literally, as I was telling you guys, I'm not going to jump. Here I am jumping, but I think it's important to know exactly what's going on here. So imagine you have these molecules, right? You have this molecular system with N atoms. Okay, our aim is to learn a generative model over a time series. So you see now you have molecular structures XI, right? So you have these molecules that have some position. So each little atom inside that molecule has some 3D position, right? That's why you have this 3N. There's some 3D position in space. And you have a trajectory of these molecules. So X1 would be the position of molecule at time 1, and then X2, position of the molecule at time 2, and so on all the way to XT. And you kind of define what that trajectory length T is. These are trajectories for short peptides and single-chain proteins, which just kind of means that they're using smaller things, right? Like probably not this. This is a massive molecule, but all the examples that they show here are these little tiny molecules. So still very much early days. They're just using very small little molecules here. Our chemical specifications are amino acid sequences, right? So very similar to tokens, where you have a limited vocabulary of tokens. Here you have sequences of these amino acids, and these amino acids, there's only a limited amount of amino acids. I thought there was more than 20. I thought there was something like 25. How many amino acids are there? 20. Okay, never mind. So there are just 20 amino acids. So you see it's 20 possible here. We adopt an SE3-based parameterization where the coordinates of each amino acid residue are described by a rototranslation, which is just a rotation translation, right? So each XTL, so each frame of this time series, XT, right? X1, X2, X3, and then L is the actual length of the amino acid sequence, is being described by this rotation here and this translation. And this little tuple here, RT, is effectively SE3. And for those of you that aren't familiar, SE3 is called the Special Euclidean Group 3, right? Which is basically a Lie group, which is a type of mathematical construct within the group theory, right? And group theory sounds kind of scary, but it's actually not scary at all, right? The way to think about what group theory is, it's kind of like a biology mindset for math, right? So if you think about somebody who studies like insects, right? Like what are they fundamentally doing is they're kind of grouping things together, right? They're saying, okay, well, this group of things here are beetles, and then we're going to have a group of things here that are butterflies, and then within butterflies, we're going to have like a moth. And then so they're basically kind of like seeing what's out there in the world and then trying to like organize them together into little groups so that you can say, okay, well, everything in this group has this specific property and everything in this group has this specific property. So group theory is just an organization of kind of mathematical concepts and ideas into different groups that have different properties. And then within those are these Lie groups, and then within that you have SE3, which is basically just the rotation and translation of something in 3D space. All right, so I have ChatGPT here. Is SE3 a Lie group? Here's a breakdown of SE3. The Special Euclidean Group 3 is a group, meaning it satisfies certain mathematical properties such as closure, associativity, identity, invertibility. The special part, blah, blah, blah. The elements of SE3 can be represented as a transformation that includes a rotation and a translation. Okay, so fundamentally, SE3 is just this R, this 3x3 rotation matrix, and then this T, which is a 3x1 translation vector. So you see that's effectively what we have here. We have this SE3 representation of this chain or sequence of little amino acids, right? So, and you also have these 7 torsion angles. But really the important part is that you're taking these molecules and defining them as rotations and translations of the previous molecules. So you're saying, okay, so here there's a translation of whatever this is, 1, and then maybe there's a rotation. Here it doesn't seem like there's a rotation, right? Here there's a translation, then this is a rotation of 0, and then here you have a rotation of whatever, like 120 degrees, and then a translation of whatever, right? So like it's a way of describing how this chain looks in 3D space by saying it's accumulating these rotations and translations, and there's some specific rotation and translation to move between each element of the sequence, right? Which is, I have some problems with this, but we'll get into it later. Let's go back up here. So they've turned this into a generative modeling task over a 2D array of SE3 invariant tokens, and they're going to be using a scalable interpolant transformer. Okay, so effectively just a transformer. We'll see later how they actually use one of these more fancy kind of Mamba RNN kind of architecture called Hyena in order to deal with a longer trajectory, right? Because transformers have this quadratic problem because of the attention mechanism, right? The computational and memory complexity grows quadratically, which means that if you have a transformer, you're going to be limited in terms of the number of frames or the sequence length, right? So using something like a Hyena or a Mamba or something like that where you can deal with much longer sequence lengths means that you can model longer trajectories. Okay. We evaluate MDGen on some unseen test peptides, and it provides realistic transition paths between arbitrary pairs of metastable states, recovering fast dynamical phenomenon below the sampling threshold of coarse time-step trajectories. Okay. Is the represented molecules mRNA? So I think specifically here they're not talking about mRNA, right? They really only say that they're doing this for short peptides and single-chain proteins. I don't know enough about biology to know whether mRNA counts as a short peptide or a single-chain protein. I feel like some RNA sequences are probably small, right? So maybe this works for some short mRNA sequences, but I don't know 100% the answer to that question. I'm sorry, God buddy. Okay. No, just proteins. Okay, so mRNA is either too big, too long, or too complicated to be part of this. Okay, but here is maybe where the first kind of pushback I have on this paper, right? Is that coming from kind of more of a robotics background, like I'm fairly familiar with this idea of kind of SE3 and kinematic chains, right? Where if you have a robot arm, it's like fundamentally you have links, and then each of those links have some rotation and translation to the other link, right? So a kinematic chain, which is just a fancy way of saying a robot arm with many different links that each rotate, you can parameterize it in this same kind of way, right? Where you have rotations and translations and rotations and translations, but that works well for robots because robots are kind of macroscopic objects, right? I don't know if that's the case for these molecules and these peptides. And here's my kind of maybe novice take on this, is that once you get small, you have to start thinking about quantum effects, right? And what do I mean by that? So in the classical world or the kind of macro world, right, things that are about as big as a robot or a human, if you had a particle and you threw it at this barrier, right, it would just bounce back, right? And you could model this with F equals ma, right? Like all the standard physics equations apply, right? And things like rotations and translations work very well in that world. But as soon as you get into the quantum world and you have to start thinking about everything as this kind of wave function, right, where there isn't actually a particle, instead there's this kind of probability of possible locations for the particle, you can get really weird effects, right? So if you have, for example, an electron, and this is electron tunneling, this is what it's usually called, you might have a particle that goes up against this barrier, and then when it hits the barrier, right, there's a small probability that the particle is now actually on the other side of this barrier. And suddenly there is a non-zero chance that the electron tunnels through the barrier, right? And this doesn't make any sense in the scale of particles that we live in right now, right? Like something the size of a human or a robot, you're never going to be able to kind of go through a wall by just kind of like phasing through it. But once you get into tiny world, this type of shit happens, right? And we have examples of like real world things where you have these type of effects. So one thing that I know that is like this is photosynthesis. So apparently photosynthesis, which is the process by which you create energy out of sunlight, right? This is what plants are doing in order to create these glucose molecules, right? You can see that this is something that's happening kind of on the scale of these little molecules. There actually is quantum effects in there, right? So here, for example, is a paper or some kind of article. Phytoplankton use quantum coherence to survive in low light habitat. Phytoplankton are shown to be able to make use of extremely low levels of sunlight by switching on and off some quantum chemical energy-saving phenomenon. Okay, so basically there's plants that have figured out some way to get light to bounce in ways that shouldn't make sense, right? Bounce in some kind of weird shit like this that allows them to kind of harvest more energy. So now my novice question is, okay, does this also apply to these molecules, right? Like, is it a valid assumption that when a molecule goes from here to here, it's effectively just a path that can be parameterized or described by just rotations and translations? Or is there weird shit that's happening at this scale, right? Like, is there like almost like tunneling type effects where like the molecule doesn't just even rotate? It's not like it's rotating and then getting to there. It's like there's like it'll like bounce in between different states, and that kind of weird tunneling or quantum bouncing and vibration doesn't fit in with this kind of base assumption. I don't know. All right, what we got? Traditional molecular dynamics approximates everything with Newtonian physics, so MD simulations are fundamentally Newtonian with some kind of force field or potential. Yeah. Okay. So maybe force field is a good way to kind of describe the kind of, I guess, classical way that molecular dynamics are done. And here is a nice little background on that. So here in the background section, the aim of molecular dynamics is this is a little typo here. I think they meant is to integrate the equations of motion, but in this case, it's the integrate the, kind of confusing. But you have some equations of motion. Here you have x double dot, right, which is acceleration. So this is m(I) is the mass. So mass times acceleration equals this gradient of u, which is the potential energy function or force field. Okay, so basically this equation right here is just F equals ma, right? Ma equals F. Okay, so these molecules are sitting inside some force field, right? And the force field is coming from all the shit around them, right? So like maybe this little molecule here doesn't like this little molecule here, so there's like a repulsive force, right? And that little repulsive force, you could think of it like a force field, right? So there's some force field that's probably very complicated to calculate, and that force field is exerting forces on these molecules, right? So maybe this little molecule wants to move this way, and this little molecule wants to move that way, and this little molecule wants to move this way, right? And really what you're doing when you're doing this molecular dynamics is you're trying to effectively get the cumulative effect of that, right? You're trying to integrate over all these little forces that are acting on all these little molecules. And ultimately, only the positions xi of the non-solvent atoms are of interest. Okay, so it's what they mean by non-solvent atoms here is that there is solvent molecules, right? So this molecule here, it's not just floating in 3D space. There's actually all kinds of other molecules here as well, right? So there's water molecules or some kind of other molecules that are swirling, right? This thing is swirling in a soup, and modeling the dynamics of that soup in which this molecule is swirling is too complicated. So we're just gonna say, okay, there's some solvent. Those things are creating some force field U, which is changing over time. And rather than trying to model the effects of all the different solvent molecules together with the molecule that we care about, we're just gonna effectively push all of that ugliness into this box that we're just going to call this force field U, and then we're going to try to figure out what the positions xi, right? Xi, the position of just the 3D position, right? 3n of that molecule, little part of that molecule over time. So this still like this is kind of what I'm saying, that it just feels like at the core assumptions here, it's like it seems like we're still a little bit far away, right? Where it's like we're just saying, okay, there's complicated shit happening. We don't really know what's going on. We're just going to say there's some force field, that there's little molecules that are made up of these little atoms or pieces, and then each of those pieces has some position in space, and then you're calculating the trajectories of those positions in space. Which is kind of like that moment, you know, sometimes people will make fun of physicists because they say things like, assume the spherical cow, right? So you're trying to do some problem with cows, and you just basically, you don't want to deal with the fact that a cow is a pretty complicated object, so you just assume a volume of sphere that represents a cow, right? So this kind of almost seems like the molecular version of that, where it's like, hey, there's probably all kinds of weird shit going on quantumly in these molecules as they interact in this like soup of different other molecules, but we're just going to assume that there are these chains that just have some actual explicit position in space for each of the little atoms, and then those little explicit positions in space evolve over time. Okay. Deep learning for molecular dynamics. So here's other people that have tried to do this. None of these papers are very old, so this is still a very new field, right? So if you look at the dates here, right, you got 2024, I think the oldest one you have here is 2019. So really, we're just at the very beginning of using generative AI and deep learning to do this molecular dynamics. And there was at least one other cool paper. So this one here, diffusion models. So actually, I pulled that one up. This one. No, this one. So this is the paper they're talking about. AlphaFold meets flow matching for generative protein ensembles. So they're using diffusion, fine-tuned on coarse-grained molecular dynamics trajectories. And look at that. This is your flow matching from generative image stuff, right? So it seems like people are trying all the different techniques that are working in Gen AI world, and they're applying them to this problem of molecular dynamics. Joint modeling of entire trajectories. Okay, what do they mean by joint modeling? Is that you're not just going from here and then going forward, right? That would just be like you're conditioning all of these with the first frame. Joint modeling is like you're feeding in this information too, right? So like you have parts of the trajectory, either the beginning or the end, or just the beginning, or multiple parts through it, and you're trying to model the rest of the trajectory using the information that you know. Okay. We build our empty trajectory under the stochastic interpolance framework. You have some continuous distribution P1, which is supposed to be the P data, right? So P data is the magical distribution you don't know, but what you do have is some subsample of that, P1. And then you have a continuous flow-based model, DX, that takes you from your prior distribution, P0, which in this case is just a normal distribution. So here, this is starting to sound a lot like diffusion models, right? You have some prior distribution, which is just Gaussian noise, right? This is literally just a Gaussian here, centered around 0 with identity. And you want to take that noise into the actual data distribution that you want, this P1, right? So your data set of images would be P1, and then P0 would be Gaussian noise. Or in this case, P0 is the equivalent of Gaussian noise for this problem, and then P1 would be your data set of like ground truth molecular trajectories. Which even that is, I kind of almost have a problem with that as well, right? Like what the fuck is a ground truth molecular trajectory? Right? Like is that even possible? Like do we actually have ground truth molecular trajectories, or do we have what we think are ground truth molecular trajectories? Right? So much like a diffusion model, right, you train a neural network. This neural network effectively tries to predict this flow, right, like this thing here. It tries to predict these little arrows here, and then once you have a neural network that'll tell you what these little gray arrows are, then all you got to do is like, okay, I'm here. What's the little gray arrow? Okay, it's this. Okay, now I'm here. What's the little gray arrow? Now it's this, right? So the same way that a diffusion model, it's basically predicting how you're moving from Gaussian noise into the image of a cat, and it's telling you kind of those little arrows or that flow. This is the same kind of idea, right? It's like, oh, that way, move this way, move this way, move this way, move this way. And then you do that for a bunch of steps, right? Each of these little steps is like an inference step of that neural network, and you'll finally get to the molecule that you want. Okay. Here's some optimal transport. When parameterized with transformers, stochastic interpolants are state-of-the-art in image generation. Okay. Yeah. Image generation, state-of-the-art is diffusion models, so I think that all checks out for me. All right, damn, you guys are popping off. Let me see. SSDs use quantum tunneling. Is this like is the peptide parasitizing the protein to change its function, but it's no CRISPR operation? I don't know. Parasitizing, that's like a pretty high-level biological concept, right? The idea of like a parasite really only exists at the scale of like organisms, right, that require energy. I don't know if you can apply the word parasite to a molecule. Like, I don't know if that makes sense. And then CRISPR is more about like a very specific mechanism to like insert and remove specific sequences from DNA and RNA. So this is not really related to CRISPR in that way. Comment from Emily here. I can't wait when they train on complexes of multiple proteins. You could train it to inpaint entire binders or given targets. Yeah, so definitely this is the early days, right? Like, because this entire paper, everything is just very tiny little molecules. And then I think Emily even pointed out that the data set that they use is actually extremely tiny as well. So like, this is almost just like a proof of concept paper. It's basically just, hey, here's how you could use generative AI to create these molecular dynamic trajectories, but like, I don't know if these are big enough molecules to like actually provide any actionable information, right? We still need to wait for a couple more generations of this, right? Wait for someone to train this on much bigger data sets, and then also use more complicated molecules, because we're limited right now by the computational and memory complexity of generative AI architectures, right? Where there's some limit here on the L, and there's also some limit on this T, right? In this paper, they do actually try, right? So they say, okay, we tried with a transformer, and there's some limit to the T here because of the quadratic complexity of transformers, and we use a Hyena, which allows us to go longer in this T, right? So they use one of the more modern architectures to get the limit on this T and extend that a little bit further. And I think they actually go from right here. So using the transformer, the SIT, you can only do 1,000 frames, but when they switch to this Hyena model, they go to 100,000 frames, right? So going from standard transformer to linear attention, or the RNNs, kind of as I call them, you can take this T and you can go from 1,000 to 100,000, right? So that's an improvement, but we still need to have improvements in this L, right? Because the L is limiting the kind of size of the molecules right now, right? If you wanted to model how some like extremely, like maybe this thing here, right? You would need a very big L, right? This number of residues, you need like a much bigger number for that. And unfortunately, we're probably just gonna have to wait for GPUs to get a little bit more advanced until we can crank up this L variable here. All right, let's keep going here. We're here, tokenizing molecular trajectories. I don't actually know why you need 7 torsion angles. I'm not even really sure what the torsion angle adds, right? So you see here how the position, each frame in this sequence, you define it by this SE3, which is the rotation and translation, but then there's also these 7 torsion angles here. I don't really know why you need these 7 torsion, like wouldn't the rotation and translation be enough? But I don't know, beyond me. I'm not even 100% sure what torsion angles even means in the context of this type of stuff here. Maybe it's like the molecule, like the bond has some rotation along the axis kind of thing, and that's the torsion angle. But I don't know, I'm just guessing. Okay. Conditional trajectory generation, meaning that there always exists at least one frame in the trajectory with unnoised rototranslations, which we do not need to generate and can reference in the modeling process. So there's, whether you're doing forward simulation, interpolation, upsampling, or inpainting, there's always at least one frame that you have, right? So this is the hardest version, is forward simulation. You only have the first frame, but for something like upsampling, you might have lots of different frames. And they're going to call these keyframes, right? Which is a reference to video, right? Whenever you're, for example, using H.264 to compress video and send it, right? Whenever you're streaming Netflix in your house, there's this same idea of like, okay, there's keyframes, and then what we're sending you is not every single frame. We're sending you just the keyframes and then offsets relative to those keyframes, right? So they're going to be doing a similar thing here. So this idea of k keyframes, T1 all the way to TK, and then they tokenize residue J in frame T, right? So residue J is like the individual token or the individual little chunk in each frame. So you can see here how XT, the subscript here is like where in the sequence of time you are, and then the J is like where within the molecule you are, right? So like where in the residue you are, and then where in the sequence of time you are. And they turn this SE3, right, rather than having rotation and translation matrices, they turn it into a unit quaternion, which is just a way of representing rotation, right? So quaternions are a very popular way to represent rotations because I think they're just more efficient. They're kind of smoother, right? So R is a 3x3 rotation matrix, right? Think about that. That's 9 numbers versus a quaternion is only 4 numbers. And quaternions also don't have a Gibel lock problem, so they're just a cleaner and more efficient way of representing rotations. And then you have your translation vectors, which is 3 numbers. So you've turned your R and T, which is 9 numbers and 3 numbers, into Q and T, which is 4 numbers and 3 numbers. Okay. And then they convert this torsion, which I still don't even know what the fuck that is, to points on the unit circle, obtaining a 7K, right, the 4 numbers plus the 3, plus 14 dimensional tokens for each residue in every frame. So each of the 7 torsion angles is parameterized by 2 numbers, which represent some point on a unit circle. To untokenize all atom frames XT, we read off the torsion angles from the unit circle and apply the keyframe rototranslations to the generated offsets to obtain absolute rotation translations. Okay, so this is how they make it SE3 invariant, right? Where if you think about like a robot arm or a kinematic chain, you could parameterize each of the rotations and translations of each of those links to some kind of world coordinate frame, right? So you could say, here's the rotation of this angle with respect to the world coordinate frame. But an easier way to do that would be to say, okay, here's the rotation and translation with respect to the previous link of the robot arm, and then that link of the robot arm, here's the rotation and translation compared to the previous link. So by having them, all of them, by having these rotation and translations be relative to the link before, or in this case, the little residue beforehand, it allows you to simplify the modeling problem and consider a greater range of architectures. Okay. How are we doing, chat? They've overloaded the term frames. There's frames of the video, 3D frames for each residue's orientation and space. Yeah. All atom frame. Okay. Generated distribution conditioned on rototranslations. You have amino acid identities A, right? This is the amino acids of which it's basically a vocabulary of 20 possible amino acids. And parameterize the velocity network. So this is the kind of like the diffusion model, right? That's telling you where to go, where to step along this field that will get you from your noise distribution into your actual thing that you want, your image of the cat, or in this case, the actual molecular dynamic trajectory, right? You can see the dimensionality of this shit is starting to get kind of complicated here. You have T frames of L length, where each L, or each little part of that is 7K plus 14, where the 7K plus 14 comes from here, right? So this is a pretty high dimensional space here. And then cross 0 to 1, because the time is defined from 0 to 1, right? So the same way that in a diffusion model, right, you're going at time equals 0 to time equals 1, right? And at time equals 0, you have the x0, which is the noise, or the Gaussian noise distribution. Then at time equals 1, you have the distribution that you want, which is the image of the cat. So this is 0 to 1 is the time. Okay. Which is discretized into T steps. The main trunk of the network consists of alternating attention blocks across the residue index and across time, and the construction of each block closely resembling DIT. This is the diffusion transformer, which actually, not this one, but interestingly, I read this morning that the guy, one of the Sora Diffusion guys actually left OpenAI and is now at Google. So the OpenAI shit show continues. Everybody's leaving. I don't know why they're leaving. You know, it's kind of part of the drama, I guess. But they do. Let me actually pull this up. So in this paper right here, they have in the appendix section, here's the exact algorithm that they're using. You can see here's all the different crap. You have your amino acids, noisy tokens, conditioning tokens, blah, 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 blah. But then here you go, diffusion transformer. So you can see the first thing they're doing here, for example, creating embedding, time embedding, right? So the same way that you can have position embeddings, you can have time embeddings. And you can see here, blah, 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 blah. And then you have some number of transformer layers. So you have a bunch of stacked transformer layers. Each of these transformer layers is this diffusion transformer attention layer. And the diffusion transformer attention layer is basically two different attentions. Here you have attention with respect to the L and then attention with respect to the T, right? So your attention mechanism requires a sequence, right? And what is that sequence? So this one here, GL attention, and then the attention is the attention with respect to the sequence in this L dimension. And then the other one is the attention with respect to the sequence in the T dimension. So that's why you have two different attentions there. And then once you have those two different attentions in each of the different dimensions, then you just feed it all through this multi-layer perceptron. So this is kind of a pretty standard transformer situation here, right? You have your attention mechanisms into a multi-layer perceptron. You have your layer norms just to make everything nice and smooth. And then you just have a bunch of those transformer blocks. Okay. Let's go back here. Alternating attention blocks, where you have the residue and the time one. Meanwhile, mask tokens are provided for the unknown frames and residues that the model generates. So masked... right, whenever, for example, you're doing a image encoder, right, like, and you're pre-training an image encoder, something very common that you'll do is you'll start from a data set of actual images, and then you'll mask parts of the images, and then the pre-training unsupervised learning task that your model is receiving gradients from is coming from trying to predict the masked parts of that, right? So you already know what the answer is, right? Because you have some data set of these trajectories. But in order to get the model to learn how to do these tasks, you're effectively going to take the final answer, you're going to mask out certain parts of it, and then you're going to ask the model to reproduce those masked missing parts. And because you already know what the answer is, right, it's a self-supervised task in the sense that you don't need to provide labels or anything because the label's just kind of inherent to the fact that you're masking it, and then you can just take what you know the answer is, which is this little patch here, and then you get what the model predicted, and then you can just compare those two via a loss function and then use that to push a gradient all the way through the model. So they're effectively just doing masked modeling to train this model. Okay, so now we know that they're using this mask model, this masking type stuff in order to train this model, but what are they actually training on? And this is the data set. So in order to train MDGen, they're going to be training on the Atlas dataset, which is around 3,000 training, 100 validation, and 100 test tetrapeptides for 100 nanoseconds. So one thing in this paper is they're constantly fucking with the delta T, right? So in between each of these frames, there's some amount of time. And you can actually have different resolutions of time here, right? So for example, when we go here and they say PS, what is PS? What is NS? Well, PS is picosecond, which is 10 to the negative 12. NS is nanosecond, 10 to the negative 9. And you can go further and further down, right? So FS is femtosecond, right? So you can see how basically for something as small as these little molecules, like the delta in time between these, you almost want it to be extremely tiny, right? Which is actually part of why there's a problem here, right? Because large separation in timescales between integration steps and relevant molecular phenomena. So some molecular phenomena might be happening in the femtosecond timescale, right? So like the molecule is like doing little things that are happening at this tiny little delta of time. So if you're limited by the sequence length, L, right, this number of T frames here, if every single frame is 10 femtoseconds, then you're basically just going to spend all of your context modeling what happens in like one little picosecond. But let's say you wanted to know what a molecule does over a millisecond, right? Then you're going to have to increase the resolution of time between these frames into something more like nanoseconds, right? So in this paper, they're constantly kind of playing with the different timescales. And that's a little bit of an issue, but you got to do what you got to do here. Okay, let's go back and look at this Atlas dataset. So I went and I found this. The Atlas dataset comes from this. This is Atlas, Protein Flexibility Description from an Atomistic Molecular Dynamics Simulations. So Atlas is a database of standardized all-atom molecular dynamics simulations accompanied by their analyses in the form of interactive diagrams and trajectory visualizations. So this dataset is freely available here, so you can click on that. This is the Atlas dataset. Welcome. Here you have Atlas holding up the world, right? Atlas is I don't know if he's a god, but he's like a Greek mythological figure that holds up the world. And you can see you have all 1,390 entries, so that's a really small data set, right? Like just from my world, like if someone said, hey, I have a robotics model and I'm trying to train this robotics foundation model on 1,000 trajectories, I'm like, that's going to be trash, right? Like you need at least 100,000 or even 1 million, right? Like, so this is very early days because this data set is very tiny. But okay, let's click on one of these. You click on one of these, you go here. This is what it actually looks like, right? So this is, here we have, it's 101 frames, and you can see it's basically the position of every single one of those little molecules inside this larger thing. And you can actually come here, you can stop it, you can run it. It's kind of hard to see exactly what's going on. Oh, start. So you see that is the data set that it's trained on. And honestly, like most of these, they almost kind of just like vibrate, right? So it's kind of like, it kind of looks like this one here. Right? Which is why I feel like this is not just not quite there, because it's like, one, not only is this data set very small, but it's also the original source of the data set is this all atom molecular dynamics simulations, which basically means that you're effectively kind of using some hard-coded classical set of equations, right? Like kind of like the Newton physics equivalent in molecules, and then using that to say, okay, well, if we calculated the physics equations for every single one of these, then this is how the particle would move. Okay, so we used effectively classical techniques to calculate this molecular trajectory, and then we're going to train a deep learning model on those classically calculated molecular dynamic trajectories. So this model, this deep learning model, it's not like it's being trained on ground truth, right? It's being trained on a simulation that we think is ground. So there's kind of a bit of an error there, right? Because unfortunately, there's no ground truth here, right? Like, I don't even know if that's possible. Can we actually create a data set of ground truth molecular dynamic trajectories? Because if we can't, we can only ever hope to be as accurate as this, right? And maybe one kind of meme here that I want to show here is, for example, there's something in the more mechanical side of engineering called FEM, which is finite element analysis. And in finite element analysis, whenever you design some object, right, maybe like an airplane wing or something like that, you'll do these simulations. And in these simulations, you'll break the wing of the airplane down into little pieces, right, little finite elements. And then you're effectively just doing classic physics equations where, okay, like this little square right here, it's getting pulled by this one, and it's getting pulled by this one, which means that it's getting pushed by this one, which means that it's getting pulled by this one, which means that it's getting pushed by this one. So these type of FEM simulations, one, they're kind of not fundamentally correct because there's probably kind of weird quantum effects that are happening in between these that you're never going to actually model by breaking it down into these little pieces and then just classically computing the whole thing. That's one problem, right? So it's not actually ground truth. It's like a kind of a approximation of ground truth. But the second problem is that it also takes fucking forever. So here you have a meme. I fucking love finite element analysis. I want to fucking change one number and wait 2 hours for the new simulation to solve. And what does this mean? It means that a lot of times when you're running these FEMs, they take forever, right? You like set it all up and then you hit go and then you have to wait like a day for it to actually compute all these things. So not only is it giving you potentially the wrong answer because you're not fully modeling the whole thing and it's not really ground truth, but it also takes fucking forever, right? Because every single one of those little equations that you have to calculate, that's your computer is just mashing away on that, right? It's mashing away. It's calculating every single little interaction kind of explicitly. So this type of stuff here is the same thing, right? These molecular dynamics probably also take a huge amount of time because you're literally calculating every single little thing that's moving, and then the result of that is not even something that you can say is ground truth. So how does this fix those issues? It doesn't fix the first problem, right? The first problem of like, hey, this isn't even ground truth. This model doesn't do that. But what it does fix is the second problem, right? So the second problem is this takes hours because you have to calculate all these little interactions explicitly. This one solves that because now you don't have to calculate all that crap, right? You basically just, the model with just a couple of inference steps will generate that for you. So that's actually a huge improvement, right? And here is the data to prove it. So here is median results on test protein ensembles, blah, 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 blah. But look at this, runtime. Here's the runtime in seconds. Here's AlphaFlow and MSA sub. Look at this, 70 seconds. So this AlphaFlow, 70 seconds, this is kind of like the classic bullshit here where you're calculating all the stuff explicitly. But MDGen, right now all you're doing is reducing it to just a couple inference passes of your neural net. Look at that. That's a 10x improvement in time. So that's a big deal, right? Because it now means that you're no longer sitting there just waiting, right? Imagine you're trying to design some new drug or understand some kind of interaction between these molecules. Every single hypothesis that you have, you're going to have to wait a day to test it because you're going to have to wait for your little molecular dynamics simulator that is doing all this explicit stuff to do all that explicit stuff. But now you can do it significantly faster, right? So even though the final quality is going to be effectively the same as the what do they call it? The all-atom molecular dynamic simulations, like you're not going to get something better than that, but you're going to get it much, much faster, which means that the kind of iteration time is going to be much, much faster, right? And you can imagine that as we're moving into a world where designing proteins and designing molecules that have specific interactions, as all of that becomes more and more automated, right? Being able to very quickly explore different paths is actually very important. And this is very similar to how when you're doing a kind of a Monte Carlo rollout, right? Right, you're doing this kind of Monte Carlo type shit that everyone is obsessed with now because of O1, but it's, people have been doing it in reinforcement learning for a long time, right? Every single one of these, imagine if every single one of these little steps, you had to do this type of shit. It's going to take a long time to explore that tree, right? But now imagine if every single one of these little steps takes only 0.2 seconds, like 1/10 the amount of time. Now you can more effectively try a lot more trees, right? And that's actually something that people do in reinforcement learning, right? The actual policy that kind of explores this rollout policy is often smaller, right? So they usually design it such that the thing that's actually going out and trying these different trajectories is actually a small, cheap model versus the actual model, right? So exploring or searching efficiently is effectively what this paper is unlocking. It's not changing the quality, it's changing the speed of it. And speed allows you to search over a larger space, and then searching over a larger space, you're probably going to find the thing that you want. Okay. Which Greek god confuses me? Is Atlas a Greek god? That's my question. Is he a Greek god or is he like a Titan? Right? I know there's like a kind of ontology, right? Where like there's an older gods, which are these Titans, and then you have like the newer gods. I don't exactly know. I'm not like super knowledgeable about the Greek god pantheon, but I just know Atlas carries the world. That's kind of all I know. He's a Titan. There you go. Okay. Our experiments make extensive use of Markov state models, discretizing its MD trajectory into 10 metastable states and estimating the transition probabilities between them. So this is kind of actually perfect timing because we literally pulled off this tree, right, which is kind of assumes the Markov property. The Markov, anytime you see that word, basically it means that you have some state and then you have some limited set of possible actions, right? So in this case, what they're saying is that each state, which is effectively like one of these frames, rather than having some continuous space of all possible things it can go to, you're going to say, no, it can only go to one of these 3 possible next states, and there's 3 different actions, or in this case, transitions that it can do to get to that state. Right, so rather than having an infinite possible next state, there's only 10 possible next, what they call metastable states, which I assume is just like states that you find the particle in or something like that, or these little molecules. And then now all you have to do is effectively estimate the transition probabilities between them, right? So the transition probabilities is effectively this number here, right? So like A1 is that 0.1 chance of going from this state to this state. A2 might be 0.8, and then this one might be 0.01 or something like that, right? So the transition probabilities are those little, like, what is the probability of going from this state to the next state, given that you're at this state? And I just don't like the Markov assumption because it just is not representative of the real world, right? Especially at the scale of, like, tiny little molecules. I feel like a Markov assumption in the scale of these type of things just doesn't make any fucking sense to me. But, okay. Let's see. Let's go back up here. Mass tokens. G, roto translations, torsions, residue identities, upsampling. What is this? Okay, this is just what you're conditioning on. So this is conditioning on basically means what you're giving your model, right? So in a diffusion model, right, you're conditioning on text, for example, right? Your diffusion process, the actual neural net that's predicting this right here, right? It's conditioned on something. What is it conditioned on? In generative image modeling, it's conditioned on a piece of text or maybe some object class or something like that. In this case, you're conditioning on the first frame if you're doing forward simulation. If you're doing upsampling, you're conditioning on a bunch of frames, right? That's the data set. We talked about the Markov state models. We obtain 100 nanosecond trajectories for each peptide to compare with ground truth simulations. This is kind of like it's not ground truth. It's some simulation. The same way that this here isn't ground truth of this beam, right? If you were to actually like bend this beam, you're going to get a slightly different answer than this simulation. So I wouldn't call FEM ground truth the same way that I wouldn't call this shit or this shit ground truth either, right? There's actually, the ground truth is like actual physical reality. And I don't even know if we can get physical reality trajectories. Is it possible to get the trajectory of a molecule that it actually is doing at the femtosecond frame rate resolution? I don't even know if we have the tech to do that yet. Maybe over time we'll eventually get that tech, but okay, so they're going to be looking at different timescales. So you see here 10 nanoseconds, 1 nanosecond, 100 picoseconds, 100 nanoseconds. So these are different timescales, and they're basically comparing the performance here. And they have some like kind of 500 IQ metrics here. Jensen, Shannon, divergence. So I think given that this is a divergence, I think lower is better, right? So 0.13, this is lower than this, so this is better. Right, a little bit better than that. This one seems better. MDGen demonstrates excellent distributional similarity to the ground truth. Okay. Forward simulation evaluations on test peptides. So here it's kind of hard to see, but basically what they want to show you is that you see how there's two things here. There's the backbone torsions, there's the blue, and then there's the orange. So I guess orange is predicted and then blue is actual. So really what they're showing you here is like, look at that. It's pretty accurate, but it's missing some of them, right? So you see how here there's this blue, there's no orange there. So it kind of just completely missed this little point right there, right? And then even here, when you look at this molecule here, this is the molecular dynamics or the simulated ground truth as they call it, and then their prediction of it. You see how there's actually some differences here, right? So like something here is different. See how that's like dark red and this is light blue? So I don't know, maybe the model's even more right? Maybe like at some point, once you actually train these on bigger and bigger data, like right now, if I had this model versus this, I would trust the classic molecular dynamics simulation more, right? But project this forward a couple years and you start training these things on bigger and bigger data sets, I'm actually going to start trusting the model more, right? Because once I feel like the ability to generalize and like predict things is going to be more powerful via a data-driven approach than this kind of like hard-coded kind of equations and then just calculate forward approach. So right now, I feel like this one is probably better. The classic MD is probably more accurate to what is actually happening, but I feel like we're only just a couple turns of the data crank away from the molecular, from the MDGen being a better, being more likely to be the actual, closer to the actual ground truth. Samples 100 nanosecond equivalent trajectories in around 60 GPU seconds compared to 3 GPU hours. There's kind of what I was saying again. This is like the most important part of this paper is just the speed, right? So much faster. You can get the full trajectory in effectively like a couple orders of magnitude faster than explicitly calculating it out. A speed up of 10x to 1000x. That's why people are interested in this right now. What do we got here? Transition path sampling results. Oh yeah, I thought this was kind of interesting. The trajectory on the 2D free energy surface. So this black line represents the trajectory, right? So every single one of these dots is like a frame, right? So if you have 100 frames, like this is frame 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So one thing that I found was kind of weird, and they have more of these graphs here, is just how wobbly it is. Right? So it's not like the molecule is like moving from here to here to here, right? It's not like transitioning in a very kind of like smooth path. It's like if you look at this path, it's like kind of bouncing around a lot, right? It kind of, I think this one probably represents it the best, right? Where the molecule is kind of like inherently kind of like vibrating and noisy, and then it just vibrates and then pops out into a different one, right? So like this here, it's not like a molecule that's like this and then goes like that, right? It's basically, it's like vibrating and then it goes, and it just like kind of like snaps, right? You see how from here to here, it just kind of seemingly snaps into the next metastable position, and then it just kind of vibrates around in this metastable position, and then it'll snap to the next metastable position, and then it'll kind of like vibrate there again. So I don't see an explanation of what the fuck this little vibration stuff is, right? Which goes back to the original kind of stuff I was talking about, where there's probably some weird stuff going on here, right? Like there's probably some weird quantum mechanical reason why like it vibrates here, and then only after it kind of vibrates in this particular way does it bounce into the next way, right? So like I'd love to get to the point where we actually kind of understand what the fuck is happening in these, like why this random huge jump occurs. Like, look at these paths. These are so weird. Like, right? Like, what is this? Did it like bounce around here and then it went up here and then it bounced back and then it went here? Very strange. Right? Like one way to think about it is like, imagine if you had to, like, you know that like internet meme where like people fill a water bottle like halfway with water and then they try to flip it? Imagine trying to model that with this type of shit here, right? Imagine doing this FEM style where you're like every single chunk of water and you have some kind of like fluid simulation and you're trying to like model exactly how the water moves when you're flipping this bottle so that it lands on the head, right? Like that is just not exactly what's going on. You're almost never going to find exactly what is going on or how it actually ends up doing that by doing this type of simulation, right? So that's kind of what I'm seeing here is the same thing. Because if you think about like the way you're measuring the accuracy of this, like how accurate are these little vibrations, right? Is the accuracy just basically saying, oh, you're kind of here and then you're kind of here and that's pretty much good enough? Or is it actually to the granularity where like you really have trust in every single one of these little bounces? Because it seems to me like these little bounces are kind of very arbitrary. Okay. I've got my critical hat on, you know? Our model enables zero-shot sampling of trajectories corresponding to arbitrary rare transitions for unseen peptides. Yeah, and this is more going to be a thing in the future, but as these models get bigger and bigger, I think they will be able to kind of zero-shot things that we're never going to be able to model, right? So like there's going to be particles that are so big that are interacting in such a complicated way that you'd never be able, there's not enough time in the universe to do this type of FEA or this type of stuff to calculate what's going on. But these models will just give you an answer, right? It'll say, okay, you have this really weird, complicated setup. This is what it's going to look like in 100 picoseconds. And maybe we never actually get a mechanistic understanding of like why this molecule does that. But from our point of view, it's like, who cares? If you can tell me that this exact molecule is the one that's actually going to turn into this weird little thing that fits inside this very specific binding site, that's all I need, right? Because the only thing that we're interested in as a human is more so kind of like, can we actually do something with this? And at that point, it's like you kind of only need the answer. You don't really necessarily care about like mechanistic interpretability in molecular dynamics space. Some molecular motions occur at faster timescales. MDGen to upsample trajectories saved per time step 10 picoseconds to a finer time step of 100 femtoseconds. Right? But like what to evaluate this, we compare the autocorrelation function. Like how are you evaluating the molecular trajectories at like 10 femtoseconds? You know, there's like no ground truth there. So like you can upsample it, but like you can't verify that, right? It's kind of like upsampling in images where you just like enhance, right? Like the reason that seems ridiculous to us is because we know that there's not like information there for you to actually keep enhancing infinitely, right? So there's kind of a similar thing here. It's like how do you know that enhance, upsample, smaller and smaller time step? How do you know it's actually like doing that? These features are completely missed. Our model distinctly recovers the oscillations of certain torsion angles. I think the oscillations is kind of what I was describing before, right? The fact that you're kind of like oscillating here. You see there's like this kind of wobbly vibration and then suddenly you get to a point or you accumulate some amount of momentum. I don't even know if momentum is the right kind of mental model to use here, but like for some reason it's like it doesn't just go from here to here. It like kind of like wobbles around here and then goes to the next one. Very weird. Okay, I think we talked about this, but we can just talk about it again. So when they were using the transformer, this SIT, they were limited to rollouts of 1,000 frames with a 10 picosecond time step. But they wanted to generate extremely long trajectories, so they replaced the time attention in the baseline SIT architecture with a non-causal Hyena operator, which has O n log n rather than O n squared, right? So this is the quadratic complexity of the transformer here. And instead, they're going to replace it with the Hyena, which is this right here. So this is the Hyena paper, Hyena hierarchy 2023, which feels like a million years ago. But look at this. This is the Tridao is the Mamba guy. So you got the Mamba guy. You got Joshua Bengio. So got some OG heavy hitters here. And this is effectively the whole like kind of like every other RNN or Mamba paper where you basically end up reading the quadratic cost and sequence length. If only we could fix that. Here you go. Hyena, a subquadratic drop-in replacement for attention constructed by interleaving implicitly parameterized long convolutions and data-controlled gating. So basically, TLDR, it allows you to increase the sequence length, right? But it's not like a free lunch, right? At the end of the day, any of these RNN, Mambas, Hyenas, like, it's not a free lunch. You're losing some of the power that transformers have, right? Like the transformers are so powerful because they have this O of n squared, right? That O of n squared means that any part of the sequence can pay attention to any other part of the sequence, right? Versus in something like a Hyena, it's kind of like a convnet, right? So now you're limited by, okay, this convolution operation that's happening. That means that you're kind of going to lose a little bit of information, right? Kind of like an RNN, right? Where you have the hidden state. You're losing a little bit of information. So these Hyenas, Mambas, RNNs, they're not like a magic bullet. You're losing a little bit of power by using something like that rather than the transformer. But the benefit is that now you can have a lot longer trajectories. So the specific part that they're replacing is the time attention in the baseline. So if you actually go here, right, here is the attention in the time. So this GT here, this is the time attention. They're going to replace this one with this one. You see, so they basically got rid of this one. They still have this one. They still have the attention with rope for the L, which is the sequence here, or the dimension here, which is like the length of the little amino acid. But they're getting rid of the attention in time, or replacing it with the Hyena, so you can do longer sequences. Where is it? Right here. Invariant point attention. But it's all pretty much the same, and I think they compare it. Do they have like an actual difference here? I mean, another thing with this paper is that, like, I just don't have bio expertise, so like I don't know what any of these fucking metrics are, right? It's almost like when we read computer vision papers, like I forget that other people might not know what, like you have like SSIM, you have like 40 different types of metrics, and like you start to get used to those metrics, but like I don't know what any of these are. Root mean W2 dist, MDPCA W2 dist, weak contact J, exposed residue J. Like, I don't really know what the fuck any of these are. So it's very difficult for me to know like how much better 0.29 is than 0.41. But I do know what runtime is. So a runtime of 0.2 compared to a runtime of 70, that's pretty strong. Okay. Molecular inpainting could be a general technique to design molecular machinery, right? So imagine if you had this, but you wanted to create something that had this kind of trajectory, right? But you don't know what molecule to fit in right here. So you're like, okay, I really want this effect, but I want a protein that's going to be on the inside ring of this, and I have no idea what that protein is going to be. You could use this model to do that, right? You could basically say, okay, well, I'm going to take this model and I'm going to blank out that part of the protein, and then I'm going to just run it and inpaint, and then we'll see what happens, right? And the model will just tell me, oh, if you want this particular motion in this particular thing, this is the specific little peptides and little like whatever these are. I don't even know the right way, residues that you need in this particular kind of configuration in order to create that effect. So that's pretty powerful. And even if this one doesn't give you the right answer, right? Like as we were saying, because this is fundamentally trained on this kind of like classical simulation type stuff, it might not give you the right answer. But because you can run hundreds of them, because they're very fast and efficient, because it's just inference on a neural net, that means you could get 100 different possible candidates. And now you have 100 different possible candidates rather than one candidate that it took you like forever to figure out. Considerations unique to molecular trajectories. Markovianity, the reversibility of the microscopic world contrasted with the macroscopic world. I think here they're just kind of being a little bit self-aware of the fact that there's weird shit going on at the molecule level that we probably can't model. So, yeah. Future availability of significantly more ground truth MD trajectory data, which I'm not even sure if we can get that. Like, whenever we have like the high level microscopes, like these, I don't even know if electron microscope is the right terminology there, but I know I've seen like images on my social media feed of like, oh, we managed to take an image of like a metal lattice, right? And you can see the little atoms in the little lattice, right? Does that type of imaging technology, does that allow you to have the time dimension as well? Can you create like videos of these molecules? And like, what is the resolution of that imaging technology, right? So can we get some kind of imaging technology that not only has the resolution of like individual little atoms and molecules, but also has the time resolution of like femtoseconds? How far away are we from that? Are we like at the millisecond? I don't actually know. Actually, you know what? You know who might know this? GPT. Let's ask GPT. GPT. Let's ask GPT for 01 preview. What is the scale in meters? Scale. What is the minimum resolution we can image for molecular dynamics with current technology? Specifically, scale in meters and time in seconds. Let's see what it gives us. It's thinking. Achieves spatial resolution in the order of angstroms and temporal resolution down to femtoseconds. Oh shit, we might already be there. Scanning tunneling microscopy and atomic force microscopy can image individual atoms and molecules, achieving sub-nanometer spatial resolution. That's fine, but I want the temporal. Ultra-fast laser spectroscopy. Femtosecond laser pulses allow scientists to observe molecular vibrations and reactions as they occur with temporal resolutions around 10 femtoseconds. I mean, damn, it sounds like we can do this. Okay, so maybe we can get ground truth trajectories. And if we just, how much is it, like, ultra-fast laser spectroscopy? Is this like, how obscure is this? Is this like something that your average college has, or is this something that like is theoretical? All right, so here's how it actually works. Excitation source, sample, polarizer. Dude, what the fuck? This is just the life of like a technical or scientific person, is like, no matter how much you learn, there's always just so much more to learn. Ultra short pulse lasers. The electromagnetic, oh, okay, so kind of how the resolution of an imaging technology is in some ways limited by the wavelength, right? So you can't measure something that's smaller than the wavelength. So in this case, it's almost like the length of this pulse determines the resolution at which you can measure the time domain. But I feel like the other problem with this is that maybe you start getting into the whole quantum effects again, right? Where if you're shooting ultra-fast lasers at some molecular system, you're probably going to impact it, right? So like the act of measuring what that molecular dynamic trajectory is, because you're like blasting it with lasers, it's not actually going to do what it would normally do, right? It would exhibit different behavior, right? Similar to the double slit experiment. So I don't know, dude. We got to wait for the aliens to give us the cool tech for us to be able to answer these questions and collect a data set of molecular dynamic trajectories so that we can train a generative AI model on these and then know what anything in the molecule world is going to do at any time scale. All right, guys, that's pretty much it. Let me see if I have anything else that I had here. Oh, yeah, I had this pulled up. So the same way that there's like weird quantum effects that literally are responsible for things like photosynthesis, there's actually people, and pretty respectable people, such as Penrose here, who actually think that there might be quantum effects in your brain, right? So like this is a way of saying that consciousness originates at the quantum level. So the materialist framework is that, okay, if you just have a neural net that is your brain and you can effectively just have the input and output of every single neuron, you can recreate consciousness that way. But because we don't really fully understand the quantum world, and in the brain, there's things that these microtubules that have quantum effects in them, you can continue to push consciousness even further down and say that it doesn't emerge from neurons in the brain firing. It's actually living at a lower level, which I think is kind of cool, but again, basically impossible to prove, so I guess it doesn't really mean anything. See anything else? I had some memes pulled up. I already showed the memes. I think that's pretty much it, guys. All right. I'm going to drink this water. I'm going to scroll through, answer some questions, and then we'll see. Damn, okay. Let me see. They can literally take weeks. Okay. AlphaFlow is flow matching much faster than MD. Okay. Atlas used for molecular dynamics. Yeah, I feel like Atlas is a popular motif just because it like he carries the world, right? So like it's an easy thing to say for your projects. It's also like I feel like Greek gods are popular because there's no copyright, right? You're allowed to say that your project is called Zeus. Nobody's going to sue you. You got my attention, pun intended. Jensen Shannon is the symmetrization of KL, so Jensen Shannon is KL divergence. Fluid simulation. Cryo-electron microscopy. Dude. Universe is Gaussian splats. I like Gaussian splats as a core assumption. You know, Gaussian splats is also kind of like a spherical cow, but I don't know, for some reason Gaussian splats doesn't seem as bad of an assumption for the 3D world as kind of like little positions that are torsion angles and rotations and translations. You could actually do Gaussian splats in this way as well, right? Imagine having a kind of a Gaussian splat where every single little splat, rather than being defined with respect to some world frame, is like defined with respect to the previous Gaussian splat. I mean, it would be like kind of a clusterfuck, but you could do it. You could have this same type of base assumption for Gaussian splats. What does the cat mean? The cat is a real cat. So on all my thumbnails, I have this cat. There's a real cat called Boo. I don't know where she is, but that's where the cat comes from. I used to put my like actual face on the thumbnails, but then I was like, I'm just like some fucking ugly dude. Like nobody wants to see that, right? But if I put a cat, now it's kind of cute. Mirror, mirror, tell me who was the prettiest in the kingdom. The cat. Can we call our project King Vespasian? I think Roman Empire or Roman Emperors is also not copyrighted. Can I? Maybe not. Maybe like, can I use Roman Emperors for my company dash product name? Or is that copyrighted? There's no way, right? You could totally do that. Yeah. Project Caesar. All right. Let's do a little summary. So here's a summary. Today's stream was generative molecular dynamics. And we basically reviewed this paper here, which was recommended to us by Amelie, who's the resident bio expert in our Discord channel. And it's basically using generative AI to model the dynamics of particles, right? So or not particles, but what is it? What is the exact terminology here? Peptides and short chains. Short peptides and single chain proteins, right? So in my mind, kind of just looks like this, right? You basically have all these little molecules. They're basically moving and vibrating in space, and we want to be able to model that, right? So given either the starting position or maybe the start position and the end position, or maybe just a couple different keyframes throughout some trajectory, we want to be able to fill in the rest, right? And why is this useful? Because it allows us to design drugs, design proteins, understand kind of what is happening at the molecular level. And in order to do that, we're basically going to take a data set, specifically this data set here, the Atlas data set, which is a data set of these molecular trajectories. It's kind of a small data set, but this data set has also been generated with kind of classic simulation methods, right? Which I don't exactly know how to describe, but I know, for example, that it's similar to this, right? It's analogous to this idea of finite element analysis, where you're kind of doing the actual work of calculating all the equations for every single little interaction, and it takes forever, right? So somebody created this data set by running each of these simulations, which took them a very, very long time. And then this team here from MIT basically took that data set and trained a neural net on it. And that neural net is now capable of giving you the trajectory that previously you would have had to basically run this simulation and it would have taken forever. But now you can just run it with a neural net by just a couple inference steps, and it's significantly faster, right? So you have almost I think they say 100x or 1000x improvement in speed, a speed up of 10x to 1000x over the kind of classic molecular dynamic simulation. So here you see, for example, the trajectory. So this is a little molecule vibrating. You can see it's vibrating, boom, and then it changes to a slightly different shape, kind of vibrates there, and then boom, changes to a slightly different shape, vibrates there, and then boom, changes. So you can see that this is the actual full trajectory of that, right? So maybe if you wanted to design a drug that went from here to here, you could use this model to sample a bunch of different possible trajectories, and then in that way have a better understanding of maybe different motifs or different little elements that you want in your drug in order to produce this specific shape that's going to fit in some specific binding site or something like that, right? I'm not a bio expert, so I'm kind of just coming up with random ideas there. But that's pretty much the paper. The way that the lowest kind of base assumption here is that any of these little sequences of amino acids can be parameterized as basically positions and then a rotation and translation with respect to the previous one, right? So they're using these SE3 Lie groups to parameterize this chain of amino acids. And then I think one other cool thing that's worth mentioning is that they use a transformer architecture, right? So the transformer with its quadratic attention means that your context length or your sequence length, or in this case, the duration of time t, is going to be somewhat limited. So they have this little extra trick of using a Hyena architecture in order to increase the sequence length here from thousands to hundreds of thousands. But that's pretty much it, guys. I think this is a cool little paper. As the reviewer says, it's novel and non-trivial. The work is very exciting and has high potential for impact, but we're probably going to have to wait a couple more years for this L to increase, right? So the bigger this L is, the more complicated the molecules and the dynamics of those we can model, and then the more this T increases, then the longer these interactions we can model, right? So imagine eventually at some point this T is so long that we can model the dynamics of like a virus coming and then creating something and then like that entire system, we can model it with a neural net, which would be pretty cool. But we're probably going to have to wait for some way to get a bigger, like multiple orders of magnitude bigger data set. And also, I think like more of a ground truth version of this, right? We actually did a little bit of searching, and there's actually ways of getting much of like high time resolution. So the data that this is trained on is like, it's not real data, it's like simulated data, but it seems like we do have imaging technology that can give you the time scale and the space scale that is required. So hopefully someone starts collecting data sets, and then we can train on those data sets, and then we can have something that basically predicts the movement of molecules, which would be pretty useful. How does this fit with Fei-Fei Li's spatial AI? I think Fei-Fei Li is known for ImageNet, and she recently got a bunch of money for a startup, and they're calling it spatial. Fei-Fei Li spatial. But I don't think it has to do with this. I don't think she's talking about like spatial intelligence in terms of like molecules. I think if I had to bet money, it's probably like robotics kind of stuff, right? Like autonomous vehicles, kind of similar, more similar to ImageNet, right? So like she's talking more about some kind of Gaussian splat world model that like basically can predict future frames of Gaussian splats. That's what I would bet money is what they're doing, but I don't actually know. I don't have any insider knowledge. I don't know Fei-Fei. Hannes Stark, this guy is a legend. So you're saying this guy is a legend? Good to know. Stumbled upon your channel. Enjoy your content. I appreciate it. Okay. That's it, guys. I don't have anything else. I'm just going to end it there. Thank you, Ashutosh, Saskia, Julien, Godbuddy, Sid, Sleepyhead, Shikan, Ed, Sarah, Emily, Yatharth, Eva. Well, scrolling. Frigo, Sotaki, Jamal, Rahul. Thanks, everybody, for listening. Hope you guys have a great weekend. And I'm going to try to blow the shofar again, but again, it's like really hard to fucking blow this. Like the hole is very tiny on this, so I have to like, all right, let me try.